Hi again, everyone, and welcome to our unit on light and spectra. In this lecture, I'll begin to introduce you to some of the concepts that will be important to understanding the light that is emitted from objects in the distant universe. In the last unit, we encountered lots of phenomena that were not as they first appeared. This outside-the-box thinking will continue with light, starting with simply what we mean by that word. When astronomers say light, we mean not just what we as humans see with our eyes, but also some types that we don't see, including infrared light, ultraviolet light, radio light, etc. Spectra are a representation of the types of light emitted by an object and their various amounts, like a recipe. A tablespoon of infrared here, a heaping cup of visible light, a pinch of X-rays. Spectra are the fingerprints of astronomical objects, unique to the object emitting them, and they can tell us a lot of things about the object, its temperature, composition, gravity, and how it's moving relative to us, among others. You might be tempted to ask how we could spend an entire unit, 1/4 of this course, just on light. And this is worth addressing up front. We spend so much time on it because our understanding of light and the processes that cause it to be emitted forms the foundation of all of astronomy. We'll begin to explore how that is true in this lecture and continue throughout the unit. Let me demonstrate why light is important by building what we call a scale model, a tool that will be very important for us in putting objects in the universe into contexts that we can wrap our brains around. In this first scale model for the course, I'd like to represent the Earth with a tennis ball. This means that we're imagining shrinking the entire enormous spherical Earth down to the size of a tiny tennis ball. This requires a bit of a stretch of the imagination, but is not as out there as you might think. In fact, we do this kind of exercise every day when we read maps. A map is a scaled down representation of the real world. This scaling down is what makes them useful. A map with a so-called 1-to-1 scale would be useless to us because distances on the map would be exactly the same size as they are in reality. Your map would be enormous, exactly as big as whatever you were trying to map. For this reason, we shrink things down by a factor of thousands or even millions so that we can wrap our minds and our pockets around them. The amount that we scale them down is called the scale factor. Here's a map of the Pima downtown campus. If you look at the scale on the bottom left, you'll see that it's marked with the distances 100 meters and 200 feet. Obviously, this line is not 100 meters long. So what does this mean? This is called the scale of the map, and it's telling us that on this map, objects that are this far apart are 100 meters apart in the real world. It might be a slightly different size on the screen of your phone, tablet, or computer, whatever you're using to watch this video. But if I measure this distance by holding up a ruler to my computer screen, it corresponds to 2 inches. For me, 2 inches on the map is equivalent to 100 meters in the real world. So obviously this isn't a 1-to-1 scale map. Otherwise, this mark would correspond to 100 real meters and would be very cumbersome. I know based on this scale that 100 meters in the real world equals 2 inches on my map. But how much smaller is the map then than the real world? Let's do a quick exercise called a unit conversion, a very useful thing to figure out the scale. Let's start with a couple of conversions. To put 100 meters and 2 inches into context relative to one another, I need to know how they relate. I can do this by using my knowledge of the fact that there are 100 centimeters in 1 meter, and that there are 2.54 centimeters in 1 inch. If I set these up the right way, I can use these two pieces of information as tools to find out how many inches are in 100 meters. To do this, I need to get rid of the old unit, meters, and turn it into a new unit, inches, using these conversions. So I'm going to multiply 100 meters by a fraction equal to 100 centimeters over 1 meter. Why can I do this? Well, because 100 centimeters and 1 meter are two different ways of saying the exact same thing. 100 centimeters is 1 meter and vice versa. So when I multiply 100 meters by this fraction, I'm actually multiplying by a number over itself. Like multiplying by 2 over 2 or 160 over 160. A fraction with the same thing on the top and the bottom is equal to 1. This fraction, 100 centimeters over 1 meter, is also equal to 1. You may remember from a math class long, long ago that you can always multiply a number by 1 and it won't change its identity. 42 times 1 is 42. A million times 1 is a million. So I've played a clever trick here. I've created a fraction equal to 1 by placing two different representations of the same quantity on the top and the bottom, and multiplied by it. In doing this, I've multiplied by 1, and without violating any of the rules of arithmetic, done something very clever, which is that I've transformed one unit into another. To see how this works, consider that same rule of arithmetic, that when I have the same thing on the top and bottom of a fraction, those things cancel one another out to equal 1. Well, if I multiply 100 meters by 100 centimeters over 1 meter, then 100 meter joins 100 centimeters in the top of the fraction. Now I have meters in both the top and the bottom, and I can simply cancel them. I've taken 100 meters as a starting point, multiplied it by a very clever version of 1, and arrived at 100 meters times 100 centimeters over 1 meter, or, canceling the meters, 10,000 centimeters. I started with 100 meters and turned it into 10,000 centimeters, but all I did is multiply by 1. So I haven't changed the quantity at all, only made you look at it in a different way, with a different unit. The absolute distance is still the same. This is how you do unit conversions. Conveniently, you can just stack them up too. I've only gotten to centimeters here, and I need to get to inches. I can multiply again by another clever fraction equal to 1 inch over 2.54 centimeters, and here again cancel the centimeters in the top and bottom of the fraction. When I do the division, this leaves me with the number 3,937 and the unit inches, which I'll round to 4,000 for simplicity. 100 meters is the same thing as 4,000 inches. Since the number that I started with, 100 meters, is equivalent to 4,000 inches, this means that the 2 inches on my map that represent 100 meters are equivalent to 4,000 real inches. Divide both sides by 2 and it tells you that 1 map inch is the same as 2,000 real inches. This is the scale of the map, 1 to 2,000. This means that if I were to blow up this map by a factor of 2,000, the map would be the same size as real objects in the map, the size of the Pima campus. That was a lot to throw at you, so let's do it again. Here's another map, this time showing all of Tucson. Now this distance in the legend, still about 2 inches on my computer screen, equals 5 real miles in this case. This is a bigger distance than the scale on the Pima map, so we should expect our scale factor to be even larger. In other words, you would have to blow this map up by a much larger factor in order to make it match reality. The conversions that I need this time are that there are 5,280 feet in 1 mile and that there are 12 inches in 1 foot. I'm going to turn each of these into a clever fraction, just like before, being careful that the unit that I want to get rid of is in the bottom so that it cancels. I can actually do all of these conversions at once if I'm careful. In the first case, I'll put feet on the top and miles on the bottom so that it cancels with the miles I started with. In the second, I'll put inches on the top and feet on the bottom so that it cancels with the feet in the top of the first fraction. Miles cancels and feet cancel, so I'm just left with inches again. Now I just multiply all of these numbers together and they give me 316,800 inches. 5 miles is the same as 316,800 inches. Let's round this to 320,000 to make it a little nicer and compare it to the 2 inches that it takes up on our map. If I divide this by 2 again, it tells me that 1 inch on this map is equivalent to 160,000 real inches. This is a 1 to 160,000 scale map. I would have to scale it up by 160,000 times to make the map the same size as the city of Tucson. Here's another case with the whole state of Arizona. The scale this time is 200 kilometers, still equal to 2 inches on my map. To turn kilometers into inches, I might use my knowledge of the fact that there are 3.1 miles in a 5 kilometer or 5K run, plus the same 2 conversions that I used last time. If I line all of these up cleverly, kilometers, then miles, then feet in the bottom, I can cancel them out each time and be left with just inches. About 8 million inches in 200 kilometers. If I turn this into a scale again, it becomes 4 million. 1 inch on this map is 4 million real inches, so the scale is 1 to 4 million. This technique will work with any map, any scale model. We won't walk through the whole thing here again, but take my word for it when I say that I used the same technique, comparing the scale on the map to the size on my computer screen, to calculate that this map of the US is a 1 to 30 million scale, and that this map of the world is 100 million to 1. As a reminder, this means that I'd have to blow this up by a factor of 100 million in order to make it the same size as the real Earth. There's not enough paper on Earth to do this, so this demonstrates again why scale modeling is useful. We've shrunk the Earth down in order to wrap our brains around it. Here's where I'd argue that this map isn't doing me much good anymore, because as you learned in the last unit, this is not what the Earth really looks like. This, the blue marble picture that I showed you a while back, is a much better representation. On my screen, the Earth is 8 inches across in this picture. The real diameter of the Earth, though, is about 8,000 miles, which, if we convert that to inches and do the same type of calculation we've been doing, only for an image this time rather than a map, makes it about 63 million to 1 as the scale for this image. This image is 63 million times smaller than the real Earth. Okay, so remember how we were going to represent the Earth with a tennis ball in our scale model? Well, all of this talk of scale modeling was really just a lead-in to this model, so that we could understand better how to set it up. A tennis ball is about 3 inches in diameter, so this is a 170 million to 1 scale model. It's 170 million times smaller than the real objects in question. In this case, the Earth being the size of a tennis ball dictates the size of every other object in this scaled-down universe. So let's start with the Moon. If the Earth can be represented with a tennis ball in this model, then how big should the Moon be? Well, as you may recall from the lecture on moon phases, the Moon is about 1/4 the size of the Earth. If a tennis ball is 3 inches in diameter, then we need something with about 1/4 of that size, or 0.75 inches in diameter, the size of a penny. Since a penny is 1/4 the size of a tennis ball, you would need 4 of them lined up to run across its diameter, just like you'd need to line 4 moons up side by side to cross the Earth's diameter. But there's more needed in this scale model. You also need to place the penny at an appropriate distance from the tennis ball in order to represent the true Earth-Moon system, accurate in their sizes and also their separation. So how far away should it be? Well, we already know the scale, so if we know the true distance to the Moon, we should be able to scale it down to find the distance in this model. The true distance to the Moon is 240,000 miles. If we divide this number by our scale, 170 million, we get the distance from the tennis ball Earth to the penny Moon in our scaled down model. 240,000 miles divided by 170 million is 0.0014 miles. This is a very small number and does not mean much as it's represented here. So let's turn it into feet using a unit conversion. Remember before we said that there are 5,280 feet in 1 mile? If we set up the conversion as we did before, we can turn this number into feet by multiplying by the conversion factor 5,280 feet over 1 mile, canceling the miles, and we're left with about 7.5 feet. So, for a proper scale model of the Earth-Moon system in which the Earth is a tennis ball, the Moon should be a penny 7.5 feet away. This brings us to a very common problem with pictures of things in our solar system. In order to fit them all into the same diagram, even when we size them accurately relative to one another, as we've done here, we still usually vastly underrepresent the distances between them. To illustrate this, consider that a picture of the Earth-Moon system where the size of the Earth and Moon and their separations are all to scale would look like this. Viewed in this way, it suddenly seems much more impressive that men have visited such a distant world. Sometime in your lifetime, I for one believe that we'll make it to Mars. So how far away would that be in our 170 million to 1 scale model? At its very closest to Earth, when both planets are on the same side of the Sun in their orbits, Mars is 33 million miles from Earth. In our scale model, this puts Mars at 0.2 miles, 1/5 of a mile from the tennis ball. Mars has about half the diameter of Earth, so it could be represented by something like a key lime, something 1.5 inches in diameter, half the size of the tennis ball. To reiterate, in order to make an Earth-Mars scale model, in which the Earth is the size of a tennis ball, you have to put Mars nearly 1/4 of a mile away. The Moon is still a penny 7.5 feet from the tennis ball Earth. Let's continue expanding this scale, but go a little more rapidly. Jupiter's diameter is about 10 times bigger than Earth's, 80,000 miles or so compared to the Earth's 8,000. 10 Earths would fit across the face of Jupiter. In our scale model, this would make it about the size of a car tire. Jupiter, at its closest, is 365 million miles from Earth, So in our 170 million to 1 scale model, it should be 2 miles away from the tennis ball. The Sun is about 93 million miles from Earth in reality, a little closer than Jupiter. Whereas Jupiter was 2 miles away in our model and 365 million miles in reality, the Sun is about 4 times closer. So that puts it about half a mile from the tennis ball. The Sun's diameter is about 10 times larger than Jupiter's, 100 times larger, therefore, than Earth's. So it should be about 300 inches in diameter in our tennis ball Earth model, the size of a large motorhome. In fact, here are the 3 objects to scale in size. This speck here is Earth. Here again, though, the distances between these objects is not accurate in this picture. If I'd used a scale that would allow me to accurately represent the distances between these planets and their sizes, there's no way it would have fit on this slide. The distances between objects in the universe are huge. So let me put up some other astronomical objects that we might care about and learn about later in this course, and where they fall in our scale model. But I'm going to do so rapidly, so we'll put them in the form of a table from here out. Here's the Moon at about 250,000 real miles and 7.5 feet in our model. The Sun at 93 million miles and a half mile, respectively. Jupiter at 365 million miles and 2. Pluto is about 10 times farther away from us than Jupiter, 3.7 billion real miles, or 20 miles away from the tennis ball in our scale model. Voyager 1, a spacecraft that explored the outer solar system in the early 1970s and then kept going towards the stars, is currently 11 billion miles from Earth and still in contact with us intermittently. It's approaching a place in our solar system called the heliopause, where the wind from our sun disperses into the more general material between the stars, called the interstellar medium. This could be considered to be the very outer boundary of our solar system, and Voyager is close to that boundary. This is the farthest any man-made object has ever been from the Earth, almost to the boundary of the solar system. A great achievement and a full 65 miles from our tennis ball Earth in the scaled down model. The next step in our model, the one that takes us beyond the solar system, is a very large step indeed. The very nearest star to us, named Proxima Centauri, is 2.5 trillion miles from Earth, or, in our tennis ball scale model, 15,000 miles away from the tennis ball. Betelgeuse, the giant red star in the constellation of Orion, is 4 quadrillion miles. That's a 4 plus 15 zeros, or 4 times 10 to the 15th power, miles away from Earth. In our tennis ball Earth model, Betelgeuse must be 25 million miles away. It's worth noting that this distance to Betelgeuse in our scaled down model is much larger than the circumference of the real Earth. So our scaled down tennis ball Earth model of the solar system is starting to get pretty unwieldy. In order to actually make it, we'd have to place the nearest stars all over the Earth. And by the time we got to Betelgeuse, we would have run out of room and would have to move beyond the Earth, beyond the Moon in fact, just to make a scaled down model of the closest stars, where the Earth was the size of a tennis ball. The center of the Milky Way galaxy is 160 quadrillion miles from Earth, or 950 million miles in our model. And the Andromeda galaxy is 15 quintillion, 15 plus 18 zeros after it, miles from Earth. This puts it, our nearest neighbor galaxy, at 90 billion miles from the tennis ball Earth in our scaled down model. Both our model and the way we're measuring distances in miles are starting to get a bit ridiculous here. Our tennis ball Earth scale model now stretches beyond the edge of our solar system, and we're introducing words for very large numbers that few of us have ever heard before. And we haven't even made it beyond the very nearest galaxies. As we'll learn later in this course, the universe is much, much larger even than that. So what's a more reasonable way to measure the large distances between objects in our universe? Astronomers tend to discuss distances to objects in terms of the amount of time that it takes light to travel them. There are a couple of reasons that this makes sense. First, light travels very fast, so that makes the numbers here much smaller, and we don't usually have to invoke words like quadrillion and quintillion to describe distances anymore. Who knows what those are anyway? The speed of light is 3 times 10 to the 8th, or 300 million meters per second. Remember how the moon is 240,000 miles away? Well, light travels 3/4 of the way, 186,000 miles, in just 1 second. 3/4 of the way to the moon in just a second. Very fast indeed. It takes light 1.3 seconds to make it all the way to the moon, 8 minutes for it to arrive at Earth after being emitted by the sun, 30 minutes and 4 hours to arrive from Jupiter and Pluto, respectively, and 18 hours for light signals emitted by Voyager 1 to arrive at Earth from the edge of our solar system. Proxima Centauri, on the other hand, is much farther away even than that. And this light-focused way of looking at distance highlights that the scale of the space between stars is very, very large. It takes light a full 4 years to get to us from Proxima Centauri. Again, the very nearest star. Light from Betelgeuse takes 640 years to reach us. So we use the units light seconds, light minutes, and most commonly light years to measure distances between objects in the universe. This brings us to another reason that astronomers like to measure distances in this way. Despite the word year in its name, the light year is actually a unit of distance, not time. However, it is intimately related to time. A light year is the distance that light travels in 1 year. 2 light years is the distance that light travels in 2 years. 100 light years is the distance that light travels in 100 years, etc., etc. This reminds us of the fact that light doesn't travel from one place to another instantaneously. That, in fact, looking at light from distant objects is a bit like looking back in time. Because light doesn't travel instantaneously, there's a waiting period between light from an object in the universe leaving its source and arriving at your eye, telescope, or camera here on Earth. Light leaving an object is a snapshot of what it looks like at that instant in time, the instant in which it was emitted. In the interval between that light leaving the object and arriving at your eye, time passes and that object may change or evolve. For this reason, astronomers often refer to the phenomenon of look-back time, the amount of time that has passed from light leaving an object to its arriving at Earth, or the amount that we're looking back in time when we look at that object in space. So when we look at light from the moon, we're looking at it 1.3 seconds in the past. When we look at the sun, 8 minutes in the past. Pluto, 4 hours. The nearest stars, 4 years or more. When we look at the center of our galaxy, the light that we see is already tens of thousands of years old, and the objects that emitted it have moved, evolved, or maybe even exploded or died since the light was emitted. Galaxies are even more dramatic. when we look at the Andromeda Galaxy, our nearest neighbor galaxy, we're seeing it as it was 2.5 million years ago. When we look at objects on the Earth, this effect is negligible. It takes much less than a second for light to travel from any place on the Earth to any other. In fact, for light to travel the entire circumference of the Earth, it takes just 1/10 of a second. For light to travel across the 30 feet or so of our classroom takes just 30 nanoseconds, 30 billionths of a second. Because the speed of light is so very, very fast, debates raged for thousands of years about whether it was infinite or finite. There were ancient Greek philosophers on both sides of this debate. Kepler thought that the speed of light must be infinite, since there was very little to impede its travel between planets and stars. In other words, because the universe is mostly empty space. Galileo, on the other hand, believed it to be finite, and even tried to measure the speed of light by having an assistant open a lantern on a distant hill at a specified time and measuring when he saw it. Of course, he did not observe a delay, since he was separated from the lantern by a distance of just a mile or so, which light traverses in 5 microseconds, 5 millionths of a second. Much too small a delay to be perceived with the measuring devices of the day. He concluded that the speed of light must be very fast indeed. Because light travels so quickly, there were no experiments that could be done in laboratories on Earth to measure it. At least, that is, until the very recent past and with very sophisticated equipment. Luckily, the entire universe can be used as a laboratory in astronomy. Ironically enough, Galileo did pave the way for the first good measurement of the speed of light by discovering the Galilean moons of Jupiter. An astronomer observing Jupiter's moon Io noticed that its orbital periods seemed to be shorter when the Earth was moving towards Jupiter than when it was moving away, which he took to be an effect of the light travel time. By Newton's time, astronomical measurements of the speed of light had pinned it down to within a few percent of its known value today. Before we move on from talking about astronomical distances, let me introduce one more term. Some astronomers prefer to use a unit called a parsec rather than a light year, and we'll use both in this class. A parsec is defined like this. If you imagine taking our solar system and placing it very far away, then a parsec is as far away as you would have to move it in order for the Earth to be 1/3600th of a degree away from the sun in the sky, as observed from your distant perspective. Let's break this down a bit because it seems really weird at first. The distance between the Earth and the sun is another fundamental unit in astronomy, called an astronomical unit or an AU. We won't be using it much in this course simply because we won't be talking about many things on solar system scales. We'll be talking about much, much bigger things like stars, galaxies, and the entire universe, for which units like light years and this parsec will be much more appropriate. Nevertheless, the Earth-Sun distance is an important scale for putting things like other solar systems in context, which is why it was chosen for the purpose of defining a parsec. So why 1/3600th of a degree? This is actually another important unit in astronomy called an arcsecond. It's an angle in the sky equal to taking an arc 1 degree across, so 1/360th of the way across the sky, dividing it by 60 to make a quantity we call an arc minute, then dividing the arc minute by 60 again to get arc seconds. An arc second is therefore 1/3600th of 1 degree. You'd need 1,296,000 arc seconds to make a circle all the way around the sky. So 1,296,000 arc seconds to cover 360 degrees. It's a very small angle, but as astronomers, we are often looking at very small patches of sky, so it makes a lot of sense. If we take these two important units, the astronomical unit, or distance between the Earth and the Sun, and the arcsecond, 1/3600th of a degree on the sky, and connect them, we get the parsec. A parsec is the distance at which one astronomical unit takes up 1/3600th of a degree on the sky, and it's equivalent to 3.26 light years. So why do astronomers like this unit better? Well, one important reason is that it's a way to connect a distance to a star to the angle that objects in a solar system surrounding it might take up on the sky. For example, in my field of extrasolar planets, we're always looking for Earth-like planets around other stars. I know that if I'm looking at a star that's 10 parsecs away, I might expect an Earth-like planet at 1 astronomical unit to be 1/10 of an arcsecond away from that star. So this relationship between the parsec and the astronomical unit and the arcsecond is convenient. This way of measuring distances is nice for exoplanet people like me, but it's also nice for people like Maria who study galaxies. It's nice for talking about big things like galaxies, both because it's a bit bigger than a light year, 3.26 times bigger, and because it's easy to add on what we call a metric system prefix. A table of metric system prefixes is shown here as an example. When we talk about galaxies, we often use the term kiloparsec and megaparsec. Here, kilo means 1,000 or 10 to the third power, and mega means 1 million or 10 to the sixth power. These terms, kiloparsec and megaparsec, are easier to say and sound nicer than kilolight year and megalight year. So we use parsecs sometimes instead of light years when we're talking about very big things. Now that we have a sense of how big the universe is and a couple of ways to measure distances, I'd like to talk a bit about how light propagates. Consider light being emitted from a spherical object like our sun and spreading out in all directions. As it moves away from its source, it becomes diluted. An object that is very bright when you're right next to it will become fainter and fainter as you move farther away. To just say it becomes fainter, though, is to discount the fact that this dimming with distance happens in a very predictable way. The brightness of a light source obeys what we call an inverse square law. We'll explore this more with an activity in class, but I'll give you the basics now. The inverse square law of light says that the brightness of a light source varies as the so-called inverse square of the distance to the source. This means that if you double the distance, the amount of light you receive decreases by a factor of 2 squared, or 4. In terms of the mathematical relationship, inverse means in the denominator, or bottom of the fraction. Inverse relationships are just ones in which increasing one factor in the equation decreases the other. You can see that more clearly if we write it down. The inverse square law of light says that the brightness of a light source, which we'll represent with a b, is proportional to 1 over the distance to that light source, d, squared. The 1 over part is what we mean when we say inverse. So we might say this another way, as brightness varies inversely with the square of the distance. The only way to really see how this works is to put a number in. Like I said before, if we double the distance to a source, then we have a factor of 2 squared, 4 in the bottom of this fraction, 1/4. Doubling the distance decreases the brightness by a factor of 4. Or objects appear 1/4 as bright when they're moved to twice as far away. Perhaps the very most important thing that you can take from this relationship is the fact that brightness does not vary directly with distance, linearly, as we say in math terms, but with the square of the distance instead. If this relationship were linear, then objects twice as far away would be half as bright. 3 times far away would be 1/3 as bright, etc., etc. An inverse square relationship is much more dramatic than that. Objects twice as far away are 1/4 as bright. Objects 3 times farther away are 1/9 as bright. Objects 4 times farther away are 1/16th as bright. It becomes more and more dramatic as you move farther away. The takeaway is that things get much, much fainter as you move away from them. As a brief aside, this is just a consequence of geometry. Distance is a one-dimensional quantity, but light from a source, like the sun, spreads out in all directions, three-dimensionally. At a given distance, the light from an object is spread across the surface of a sphere, with a radius equal to the distance to that light source. Two-dimensional areas, like the surface of the sphere, have areas related to the square of their radius, the distance to the source. This is why brightness is related to the square of the distance and not just the distance or the distance cubed. We already talked about how large the distances between objects in our universe are, and now we've learned that light spreads out very quickly after leaving a source. Put these two things together, and the fact that we detect any light at all from distant sources should be pretty remarkable. Stars and galaxies are giving off so much light that even though the amount gets diluted very quickly as it moves away from its source, some of it still arrives at Earth. A galaxy emitting a certain amount of light as viewed from Earth emits the same amount of light across a giant two-dimensional sphere centered on that galaxy. An observer living anywhere along this spherical surface would see this galaxy at the same brightness. If we lived a little farther away from it, on the other hand, that same total amount of light would be spread across an even larger spherical surface, making it appear even fainter. This brings me to another thing we'll need to think about as we consider objects in the distant universe. The brightness of an object, as it appears to us, is related not just to how far away it is, but also to how bright it was in the first place, before its light started spreading out. Brighter objects give off more light in general. Consider this as an example. You're driving at night, and you see a single faint light in the distance. You don't know, can't know, whether this light is being emitted by a motorcycle farther down the road with a bright headlight, or by a much dimmer handheld flashlight being held by someone at the side of the road, close by. From a distance and without any other information, these two light sources are indistinguishable. A bright source far away and a dim source close by may appear the same from your perspective. So when we detect light from a distant star or galaxy here on Earth, we have the same problem. Say we see a bright star in the sky. We don't know whether it's a very intrinsically bright but distant star or a much fainter nearby star. So we have to use other tricks to distinguish between these two scenarios. If we can find out either how far away the object is or how bright it is, not just how bright it appears to be, but how bright it really is, we'll automatically find out the other quantity. In other words, if we know how bright one type of object or event really is, then we can find out its distance by measuring how bright it appears. Conversely, if we measure the apparent brightness of something, and we know how far away it is, then we can find out its absolute brightness. In astronomy, we use the term luminosity to describe absolute brightness. Since light is a form of energy, we'll learn how in a later lesson, we define luminosity as the amount of energy given off by an object per unit time. Note that the distance, and therefore the apparent luminosity of this object might vary, but the luminosity itself is something that's independent of distance because it's the total amount of light given off in all directions. This brings me to almost the end of the lesson, so let me recap. In this lesson, we learned that the distances between objects in the universe, even just the distance between the Earth and the Moon, are much bigger than most people imagine them to be. We wrapped our brains around this by using a mathematical tool called the unit conversion to make a scale model of the Earth-Moon system. In this model, the Earth was the size of a tennis ball, and the Moon was the size of a penny. They were separated by 7.5 feet. We placed other objects in our solar system and in the universe at large on this same scale. By the time we got to distant objects like nearby stars and galaxies, even our very scaled down model, where we represented the Earth as a tennis ball, took up way more space than is available here on Earth, indeed in our entire solar system. Our scaled down model was bigger than our solar system. The takeaway here is that they call it space for a reason, because the universe is very, very large. In making our scale model, we started with units of miles, but these became cumbersome very quickly, and we had to use crazy words like quintillion to describe distances. To correct this problem, we introduced the concepts of light years and parsecs. A light year is the distance, 6 trillion miles, that light travels in a year, which is a very, very large distance on human scales, but is only 1/4 of the way to our nearest star. The nearest galaxy is 2.5 million light years away. We introduced the concept of look-back time as well, as another way to look at these large distances. If the Andromeda galaxy is 2.5 million light years away, that means that it took the light we see now 2.5 million years to get to us. Since the Andromeda galaxy has continued on its merry way, doing all of the things that galaxies do since then, we're seeing it as it was 2.5 million years in the past. In order to know what's happening in the Andromeda galaxy now, today, we'll have to wait another 2.5 million years for the light being emitted from it now to reach us. We also introduced the concept of a parsec as a distance. This distance is equal to 3.26 light years and is defined as the distance at which one astronomical unit, the distance between the Earth and the Sun, would subtend, take up, 1 arcsecond, 1/3600th of a degree. We use this distance because A, it's a little bigger even than a light year, and B, it's easier to add a metric system prefix to, as in kiloparsec or megaparsec. We then discussed how light spreads out from its source according to an inverse square law. This law states that brightness is proportional to 1 over the distance to the source of the light squared. This means that it drops off very, very rapidly as you get farther away. We also connected the apparent brightness of an object to the 2 factors that influence it: distance to that object and its absolute brightness. We use this idea to distinguish between the apparent brightness of an object and its absolute brightness. We will use all of these concepts: scale modeling, look-back time, light years, parsecs, inverse square relationships, the propagation of light, and the difference between absolute and apparent brightness in the rest of this course, in order to understand light that's emitted from objects. This brings me back to my original question: why do we care so much about light in astronomy? Well, as we saw in our scale model, the moon is very far away. It was a great human achievement to make it there. The distance to the nearest planets is even farther. Humans may make it to Mars in our lifetime. Human-made spacecraft traveling through the solar system for 40 years are just now making it to the edge of our solar system. We learned that the nearest stars are much, much farther away even than that, not to mention the nearest galaxies. For the vast majority of objects in the universe, light is the only thing we're ever likely to get from them. We won't be sending humans, or even human-made spacecraft, to distant stars and galaxies, at least not in the conceivable future. So we have to make do with light. The light we gather from distant objects here on Earth was emitted by those objects long ago and has traveled great distances, spreading out all the while. So we're lucky that we get any at all. Over the history of astronomy, astronomers have perfected a number of clever tricks to squeeze every possible bit of information out of the tiny bits of light that reach us from distant objects. It's these tricks that we'll talk about in the rest of this unit, and we'll then use throughout the remainder of the course to understand how we know what we know about objects in the universe. Everything we know, we learned from light.